Hello, my name is Takashi Nakayama of Anritsu Corporation's Sensing and Devices Company. Today I am going to talk about the basics and applications of superluminescent diodes and why they are the attention of focus for optical sensing applications. This is what we'll talk about in this web seminar, which covers an introduction, SLD Basic, their characteristics, and SLD Unit. We'll end with an explanation of SLD application fields. Okay, let's start. Our company uses compound semiconductors as a key technology for developing and manufacturing optical devices, electronic devices, and swept wavelength light sources. We are progressing with development of devices for medical, industrial, environmental, and precision measurement applications. The business vision of the Anritsu Group is summarized as advancing beyond measurement to connect the future. This webinar presents some examples of measurement applications for SLD light sources and explains their use in sensing applications according to this business vision. Here is a simple graphic explaining the usage fields for SLD. The horizontal axis indicates wavelength from 800 nanometers to the near infrared at 2000 nanometers. Wavelengths shorter than 800 nanometers are visible to the human eye. Wavelengths longer than 2000 nanometers and strictly speaking above 2500 nanometers are called the mid-infrared. The near-infrared region is split into three application fields. The red ovals in the graphic indicate medical applications, orange indicate industrial applications, and blue is everything else. Typical short-wavelength medical applications include ophthalmic OCT, scanning laser ophthalmoscopy, refractive index angle detectors, and eye long-axis length measurement equipment. Long-wavelength applications include dental OCT, blood vessel OCT, and blood glucose sensing. In industrial fields there are applications in microencoders, scanning microscopes, semiconductor wafer thickness inspectors, aerobic inspection equipment, industrial OCT, and displacement meters. In other fields, applications include LiDAR used by self-driving vehicles. In particular, wavelengths of 1400 nanometers and more are described as eye-safe, so LiDAR automobile applications commonly use wavelengths of 1550 nanometers. Moreover, wavelengths between 1500 and 1700 nanometers have good absorption characteristics for different gas species, so they are used by gas sensing detectors. The lower part of the figure shows the SLD spectra. Short wavelength SLDs use the 800 nanometers band, and long wavelength SLDs use the near-infrared band from 1300 to 1600 nanometers. The rest of this webinar explains SLD is used in these application fields. The next part explains the basics of operation, the features, the principle of light emission, manufacturing, and reliability. SLD is the abbreviation for superluminescent diode. Some other region use the term SLED, meaning superluminescent light emitting diode for the same thing. There are three answers under the heading SLD for optical sensing. Reason why the attention now? Please remember these today. First is high output, second is low coherence, and third is easy fiber coupling. I'll explain these three answers in the following slides. This slide shows the differences between LD, SLD, and LED. There are three types of semiconductor light-emitting devices: the laser diode LD, the superluminescent diode SLD explained in this webinar, and the light-emitting diode LED. The top row in the figure shows across the section of each device. Laser diodes have a coating film on both facets forming laser chip for amplifying light by reflection and resonant within the device, and emit the stimulated emission light. The LD spectral width is quite narrow and less than a few nanometers. As explained later, the coherence length due to the spectral width ranges from several tens of centimeters to a few meters, and this optical signal is easily affected by interference. The optical output power is a few hundred milliwatts, and the output facets of the device can be easily coupled via a lens to optical fiber. On the other hand, LEDs emit light from the surface. The emitted light is similar to spontaneous emission with a broad spectral width of a few hundred nanometers. With a wide spectral width, the coherence length is just a few micrometers, so these devices are characterized by low coherence. The optical output power is up to several milliwatts with extremely weak light. Since light is emitted from the surface, LED is difficult to couple with optical fibers using a lens. The SLD introduced here have an anti-reflection coating on both facets, but an LD-like oscillator is not formed in the device. As explained on the next slides, light is amplified in the waveguide, and the emitted light is amplified by spontaneous emission. The spectral width is from 10 to 50 nanometers, with a coherence length of 10 to 80 micrometers, and an optical output power of about 10 milliwatts. As a result, the spectral width and optical output power of SLDs is between that of LD and LED. Moreover, like LD, the light-emitting facets of SLD is easily coupled to an optical fiber using a lens. The next slide explains the light-emitting principle of SLDs. Semiconductor light-emitting devices use different substrates depending on the required wavelength. In SLD, the semiconductor substrate is gallium arsenide for short wavelengths of 0.8 nanometers and indium phosphide for long wavelengths. The diagram on the middle right shows the cross-section of the SLD light-emitting layers. The SLD has the active layer, which is the same as an LD. First, spontaneous light is emitted by the active layer. LED outputs this spontaneous emission as is, but in SLD, the generated spontaneous emission passes through a waveguide formed in the active layer where the light is amplified, and ASE light is output from SLD. This amplification occurring in the SLD, but not in the LED, is the big difference between the two. We can say that the big difference between LD and SLD is whether optical oscillation occurs in the waveguide. If oscillation occurs, the occurs of laser oscillation prevents generation of ASE light over a wide wavelength range. The diagram on the right shows the structure for controlling oscillation. The first basic countermeasure is an anti-reflection coating on both facets. In addition, the waveguide angled configuration with a window region suppresses the return of light reflected by the facet to the waveguide. Next, we'll look at the three features of SLD. This first slide explains the high output feature. In the LED, ASE light generated by the active layer is output as is from the top surface. As explained previously, in the SLD, spontaneous emission generated by the active layer is amplified in the waveguide to output ASE light. On the other hand, returning light in LD creates oscillation in the device. Accordingly, LD has the highest optical output, while SLD emit light with a power between LD and LED. In comparison to LED, SLD has a high output power plus the advantage of high sensitivity in sensing applications. This slide explains the low coherence as second feature. Coherence means the property that waves can interfere with each other, a coherent property. The top left side of this figure shows a Michelson interferometer. Light from the SLD is split into two paths by a half mirror. The blue path shows the light returning from the object to be measured to the PD, while the red path shows the reference light returning from the reference mirror to the PD. The reference mirror is moved back and forth to obtain the strongest interference when the optical path lengths match, and is then moved until the interference disappears. The coherence length L is the point up to which there is still interference, and is expressed by the equation at the bottom of the figure using the center wavelength lambda c and spectral width delta lambda. From this equation, clearly L becomes smaller as delta lambda becomes larger. For example, the coherence length is 14 micrometers for an SLD with a center wavelength of 840 nanometers and the spectral width of 50 nanometers. The slide also shows a comparison with DFB laser with a narrow spectral width and indicates that the coherence length is 300 meters for 1 MHz DFB with a center wavelength of 1550 nanometers and spectral width of 8 femtometers. Accordingly, low-coherence SLD is largely unaffected by noise and have the merits of good resolution for interferometry applications as well as small noise. This slide explains the fiber coupling as third feature. The spatial coherence of LD and SLD devices is high and features high directivity. As a result, it can be collected by a lens as easy coupling to an optical fiber. On the other hand, the low spatial coherence of LED devices makes it difficult to focus the light. Accordingly, the high spatial coherence of both LD and SLD makes them easy to couple to optical fiber using a lens, which offers the advantage of using fiber to transmit from the light source to a remote test location. This slide summarizes the features of SLDs that make them ideal for optical sensing. First, the high optical output has the merit of high sensitivity. Second, the low coherence has the merit of high resolution. Third, the easy fiber coupling has the merit of easy handling. The next slide explains SLD manufacturing methods. The diagram on this slide shows an exploded view of a butterfly module. We perform semiconductor processes from growing the wafer crystal to fabricating the SLD chip in-house. These SLD chips are mounted on chip-on-carrier assembly. This figure shows the post-processing assembly of the butterfly module. The SLD COC and PD are assembled on the base plate, and a thermoelectric cooler is installed on top to control the chip temperature. All assembly is automated. The next stage is bonding the lens and isolator and sealing the cover seams. At the final stage, the fiber optical axis is adjusted and bonded automatically to complete assembly of the butterfly module before proceeding to aging, inspection and shipping. Bottom photographs show the automatic assembly machines. This slide explains the reliability testing. Anritsu has long experience in manufacturing high-reliability modules for pump laser for long-distance telecommunications. The SLD manufacturing process is the same, and we test reliability based on the Telcordia GR468 standards for telecommunications devices. With respect to chip reliability, stable operation is confirmed by performing high-temperature tests at an ambient temperature of 70 degrees Celsius for 5,000 hours automatic power control at a fixed optical output power of 5 milliwatts. The graph on the right of this slide shows the elapsed time on the x-axis and the operating current on the y-axis. When the lifetime is defined as 1.2 times operating current, median life is about 100,000 hours, which is a sufficiently long operating life in sensing equipment. From here on, I'll explain the characteristics of short and long wavelength SLDs. This table shows the characteristics of two types of short wavelength SLD. The AS8B115G230M in the top line has a spectral width of 14 nanometers, while the AS8B115L240M in the bottom line has a wider spectral width of 50 nanometers. The graph on the left shows the optical output with forward current on the x-axis and optical output power on the y-axis. The graph on the right shows optical spectra, and the blue line is the plot for the narrow spectral width AS8B115G230M, and the red line is for the wide spectral width AS8B115BL240M. The blue spectral width plot calls near Gaussian, while the red plot bimodal covering an extremely wide spectral width. This slide shows long wavelength SLD characteristics. The wavelength bands are 1.31, 1.55, and 1.65 micrometers. The 1.31 micrometers AS3B119GM10M has an optical output power of 15 milliwatts and a spectral width of 55 nanometers. The 1.55 micrometers AS5B125EM50M has an optical output power of 25 milliwatts and a spectral width of 60 nanometers. The AS5B310KM50M marked new is a new product released in 2021. It is a reasonable version with a fixed forward current specification for customers not requiring high optical output. The wavelength and spectral width are the same as the above two products and, as explained previously, the coherence length is the same with about the same resolution for interferometry. The 1.65 micrometers AS6B118GM50M in the bottom row has an optical output power of 10 milliwatts and a spectral width of 70 nanometers. The graph at the bottom left is a plot of optical output, while that on the right plots the optical spectra. As shown, this model lineup covers a broad range of wavelengths from 1300 to 1650 nanometers. The next slide explains package types. This slide introduces three package types. The first is the CAN type, which emits as a spatial light. The package form is simple and easy to use for low-cost applications. Next is a cylindrical type emitting light into a coupled optical fiber. Last is the butterfly module type. It incorporates a built-in thermoelectric cooler and maintains the SLD chip at a constant temperature. The CAN and cylindrical types suffer from changes in characteristics due to external temperature change. The top graph shows the change in optical output power between 0 degrees Celsius and 80 degrees Celsius. It is clear that the output power drops as the temperature increases. The bottom graph plots the spectra, showing a shift in wavelength to longer wavelengths as temperature increases. Conversely, as shown in the bottom graph for the butterfly module with built-in TEC, there is almost no change in characteristics as the external temperature changes between -20 degrees Celsius, 25 degrees Celsius, and 70 degrees Celsius. Next, I'll explain SLD unit type products. This slide shows an Anritsu's SLD unit with built-in driver circuit. The photographs on the left show the external and interior appearances with a butterfly SLD light source on the board. The external dimensions are 100 by 80 by 26 mm, and the external control uses a D9-pin connector. The optical output is via a single-mode fiber, as shown in the circuit block diagram. The control circuit controls the SLD module current and sends a signal to the TEC circuit. The optical output from the SLD module is monitored by this PD to maintain the output power constant. Here are the characteristics of the unit operating on a 5 DC voltage supply. This model has a wide spectral width of 50 nanometers as described previously. This is the output stability. In the graph on the right, the x-axis is time, and the y-axis is change in optical output, showing that the stability is extremely good with a change of less than 1% over 8 hours of operation in one day. The next slide shows some actual results using this SLD unit with driver circuit. This slide shows a Michelson interferometer and SLD unit with built-in driver circuit following the block diagram on the left used for OCT measurement. OCT is the abbreviation for optical coherence tomography for capturing an optical interference cross-section of materials. Light from the SLD light source is split by a coupler, with one beam passing to the DUT and the other beam returning from a reference mirror. The two returning light beams from the DUT and reference mirror are coupled and monitored to form an interferometer. The photographs on the right show a test setup. Light from this unit is split by this coupler to illuminate this DUT and return from this reference mirror back to the coupler for monitoring. Let's look at some actual measurement examples on the next slide. Here are some tomograms of living materials. The picture on the left is a leaf, and this is the cross-section tomogram in the x-axis direction with the y-axis showing depth. The leaf veins are clearly visible. The top right shows an example of an onion with clearly visible layers. The bottom right shows a feather. We can easily see the center quill and the barbs branching from the center. In the previous example, the system was configured using an external interferometer, which can also be built into the unit to eliminate the need for an external interferometer. Prototype unit is able to be prepared, so please contact us if you would like to evaluate it. Now, we'll move on to explanations of the application fields. There are various SLD covering the near-infrared from 800 to 2000 nanometers. Here are some application examples in the medical, industrial, and other fields. First, let's look at medical applications and explain why use the near-infrared. Reason is that there is an optical window into living materials. This graph shows wavelength on the x-axis and absorption on the y-axis. The red plot shows the absorption of hemoglobin contained in red blood cells, and the blue plot shows the absorption of water. Hemoglobin has strong absorption at short wavelengths, but the absorption becomes weaker from 700 nanometers. Conversely, water has strong absorption characteristics at wavelengths longer than 1000 nanometers. Both hemoglobin and water have fairly weak absorption characteristics in the region between 700 and 1000 nanometers. This region is called the optical window into living materials, and light sources emitting light at these wavelengths are used in medical sensing applications. Let's look at optical coherence tomography. As explained previously, the Michelson interferometer uses time domain OCT by measuring by sweeping the reference mirror back and forward over time. Conversely, there are other methods called Fourier domain OCT with spectral domain OCT and swept source OCT, in which the SLD light source is used in the spectral domain. The figure at the bottom left shows an example of the SDOCT optical system. Light from the SLD is split by a half mirror with one beam passing to the eye and the other beam passing to a fixed reference mirror. The reflected beams pass back to a detector where the cross-sectional reflected light distribution is observed. In addition, moving the beam laterally can be used to create a cross-sectional image of the retina. This setup has the advantage of supporting real-time, non-contact observation. The photograph at the bottom right shows a cross-sectional image of the retina with the fundus at the center measured by our SLD. This can be used to clearly observe a separated retina. As explained previously, using an SLD with a wide spectral width and short coherence length supports high-resolution observations. This slide shows some other ophthalmology equipment applications. Typical examples are equipment for measuring the long axis of the eye, which is necessary before a cataract surgery to design a plastic lens with the optimum focal correction before implantation. This method of optical interferometry measures the corneal, aqueous humor, and fundus oculi distances. As with other OCT types, these are all non-contact measurements. The photograph at the bottom shows equipment for measuring index of refraction and corneal radius of curvature. The inspection light passes through the pupil to illuminates the retina to calculate the eye refractive power and the corneal radius of curvature. The next two slides show some industrial applications. This is the atomic force microscope using a probe at the tip of a cantilever. The diagram on the right is a magnified view of the probe part. The cantilever moves vertically due to the interatomic force between the probe and atoms at the material surface. Illuminating the back face of the cantilever with light from an SLD and detecting the reflected light detects displacement using quad split PD and optical displacement detector to observe the surface of the material with extremely high nanometer order precision. The next slide explains the advantage of using an SLD. The SLD has very low speckle noise. The top diagram shows observation of light reflected from a light source by a reflective surface. The bottom diagram shows observation of light passing through a multimode fiber. High coherence laser light suffers from changes in intensity in time and space due to susceptibility to noise. On the other hand, low coherence light is resistant to noise and provides a clear noise-free image. When considering light reflected from the cantilever of the atomic force microscope cantilever described on the previous slide, the reflective surface in the top diagram of this slide is the back face of the cantilever, and light reflected from the surface has very little speckle noise, which is an advantage of using an SLD as the light source. Another application field is in optical fiber sensing. The FBG sensor is one type of fiber sensor for measuring distortion and temperature. The FBG name comes from the use of a fiber Bragg grating in the fiber path. Light with wavelength corresponding to the grating pitch is reflected and returned by this grating. When injecting probe light from an SLD, only light with wavelength corresponding to the grating pitch is returned. Any changes in the grating refractive index due to distortion and temperature change the wavelength of the returning light. These wavelength changes are used to sense distortion and temperature. This slide introduces an FBG sensor monitor using AWG as an example of an FBG application. AWG means an arrayed waveguide grating. As shown in the figure at the top right, the grating splits the light wavelengths. The figure at the center shows how the AWG splits the light into 64 channels. Injecting SLD light into the FBG sensor splits the returned light into 64 wavelengths corresponding to the 64 AWG channels. Since there are 64 waveguide paths at the output side, the PD array has 64 corresponding channels to measure the power of the received light. The FBG wavelengths are calculated from the optical powers at this PD. The prototype unit measures at a high sampling speed of 800 kHz. The next slide shows some results. In this setup, 3 FBG sensors are attached to a plastic board. The sensor arrangement is described as FBG1, FBG2, and FBG3. The board is subjected to mechanical shock by dropping an object on it near FBG1. The board distortion due to the mechanical shock changes the wavelength of the light returned from each FBG. The figure at the bottom left shows these changes, which are magnified in the graph on the right. The effect of the shock wave reaches FBG1 first. Then the wave reaches FBG2 causing a change, and finally the wave reaches FBG3 causing a change. This is not due to the order of the FBGs in the fiber, but is observed as a result of the propagation of the shock wave over the distances to the FBGs. This is the basis of measurement with FBG sensors using an SLD light source. Gas sensing is another application example. This gas sensing application using near-infrared light uses a tunable diode laser absorption spectroscope. The absorption spectrum of one line can be measured using a DFB laser emitting light with a narrow spectral width. Anritsu already manufactures 1653 nanometers DFB lasers used in TDLAS gas sensing equipment for methane. This slide shows an example using a 1.5 micrometers SLD to detect atmospheric carbon dioxide. Differential optical absorption spectroscopy is used to separate the absorption spectra of gases in the atmosphere. This figure shows the absorption spectrum for CO2, which can be detected by separating out this absorption spectrum. In this example, the light was reflected by a detector at a range of 6.4 kilometers to monitor the average density of CO2 observed in the light path. A high-output SLD is best for this application because the monitoring light travels long distances. I'll explain summary as a last topic. And here is summary why SLD is ideal for optical sensing. There are 3 key points. First, they offer high output supporting high sensitivity measurement. Second, their low coherence supports high resolution measurement. Third, easy fiber coupling facilitate easy to use. The last point is reasons why are SLDs now the focus of attention. As you all know, the demand for medical optical sensing applications is increasing as our society becomes older with longer lifespans. In industrial fields, advances in DX, the switch to digital technologies, and appearance of smart factories are also increasing the need for optical sensing. Moreover, optical sensing technologies, such as LiDAR, are in high demand for development of self-driving vehicles. In these circumstances, today's society needs more optical sensing technologies, resulting in the focus on SLDs. Thank you for your attention.